In this lecture, we will discuss the Weierstrass theorem. In fact, in the previous lecture, we have established the three relations A, B, C. The relations was A was that E is compact, E is closed and bounded, sorry, E is closed and bounded set. Second was E is compact, and third is every infinite subset of E has a limit point, in E. So, these three conditions we have listed, and we have proved in the last lecture. We have shown that the first condition A implies the second condition B, and second condition B implies the third condition C. So, first before starting for going for the Weierstrass theorem, we will first prove that C implies A. So, that all three conditions A, B, C are equivalent. It means, when E is closed and bounded set, then E will be compact, and every infinite subset of E has a limit point in E. So, all three are equivalent conditions for that. Okay. So, in this lecture, we will first show that C implies A, that is, the conditions A, B and C are equivalent conditions, In fact, once we establish this condition, then automatically this will prove, or this will establish Hahn-Vannock theorem, sorry, Hahn-Borel theorem, This will establish Hahn-Borel theorem. Okay. Now, we will discuss Weierstrass. Now, we will discuss Weierstrass theorem. Thank you. Now, to show C implies A, this we prove by contradiction. So, given that every infinite subset of E has a limit point in E. Okay. So, C is given, that is, every infinite subset of E has a limit point in E. This is given. Okay. So, we wanted to prove A is closed, E is closed and bounded, but suppose E is not closed, not bounded, let us see first, not bounded. It means, if it is not bounded, it means there will be a sequence of the points in E, whose bound will go to infinity, means each x 1, x 2, x n will be there, such that mod of x n will be greater than any arbitrary number n. So, we get then E contains the points x n with the property that mod of x n is greater than n when n is 1, 2, 3 and so on. X 1 will go greater than 1, x 2 so the limit of this x n will not exist. So, let S be the set of all such x n such that x n is greater, the mod of x n is greater than n. Then obviously, this is an infinite set, because if it is finite, then we can get the bound for x n. So, it is an infinite set, and clearly it has no limit point and has no limit point in R k. This is the set we are choosing in R S concept. So, once it is, so it has no, hence has none in E and hence not in none in E. Mean this sequence will not have any limit point in E also. Okay, that is one thing. Okay, thus is bound. So, but what is this? This contradicts C, which contradicts C, because C says that if you take any infinite subset of E, it must have a limit point in S is an infinite subset of E, but it does not have a limit point in C. So, this implies that E is closed. Again, to show E is bounded, so suppose further assume C holds, but E is not closed. It means the limit point of the E, all the limit points is not in E. So, thus we can get the limit point, then there is a point, then there is a point, say there is a point, suppose x naught belongs to R k, which is a limit point of E, but which is limit, but not a point of, but does not belong to E, because all the limits point does not belongs to E, because E is not closed. So, if it is not, then we can get this sequence of the points in E, that is, so the set x n belongs to E such that mod x n minus x naught can be made less than say 1 by n. This collection will be there, is it not? So, set of all points E which satisfy this a sequence will be obtained via this. Now, let us find S be the set of those points. Let S be the set of those points of each which satisfy this condition. Okay. We claim that S cannot has x naught as a limit, S has no other limit point, S has no other limit points, S with no other limit point except x naught, because if suppose y is another point of this, suppose if y belongs to R k and y is different from x naught is a limit point, suppose, then we get then the distance between x n minus y, because if y is a then the limit point we will just go, because suppose y is another point which is different from x, then we can say x n by n is greater than equal to x naught minus y minus x n minus x naught. Thus, by but x naught minus y, because x naught and y naught is different. So, we can just put it as it is x naught minus y. Now, x n minus x naught is less than. So, minus of this is greater than minus. Now, n we can choose in such a way, so that the whole thing this is greater or equal to. the whole thing is greater than or equal to half of this. Now, y and x are different. So, this is fixed point. It means that this as n tends to infinity, x n does not go to y. So, this implies the limit of x n is not y. So, it cannot have a point other than x naught as a limit point, but x naught is a point which does not belongs to our set E. So, this sort y is not a limit point of any, thus has a no limit point in E. Thus, S has no limit because x naught is not in E. So, S has no limit point, in E, hence contradicts our assumption 3, which contradicts C. Therefore, our E is closed. So, equivalence of 1 and 2 will implies the Hahnemann theorem. B will imply Hahnemann theorem. That is the proof for the Hahnemann theorem can be. Okay. Now, here we put some remark. The remarks say that in an arbitrary metric space, X D, the conditions B and C are equivalent. B and C, but A does not. It means in general B and C, A does not imply, but A does not imply B and C in general. It means for arbitrary metric space, the compact set and the infinite subset of E has a limit point are equivalent, but if a set E is bounded and closed, then you cannot say whether it remains compact or it will have a infinite subset of E will have a limit point in E. It is not, may not be true. For example, if suppose I take X as a Hilbert L2 space, L2 space means set of those sequences A n such that sigma mod A n square 1 to infinity is finite in L2 space. And if I take the sequence E n as 0, 0, 0, 1, 0, 0, this is the points belonging to L2 space. Now, if we take the norm of E n, now here norm of this, if suppose this I denote by A, then norm of A, of course, this is a case of function analysis, but I will, so we are not much going in detail, but this is the norm. So, norm of E n is 1 for each n. Therefore, E 1, E 2, E n, this set is there, E 1, E 2, E n and so on. Then each point having norm 1, is it not? So, it is bounded. So, S is bounded and none of the point is a limit point. No point is a limit point, because it is a point set only, limit point of S. Therefore, we can say all the limit points of S belongs to S. So, this shows H is closed also. So, it is a closed angle, but it is an infinite set. So, we cannot cover it by means of a finite subcover, but S cannot be covered by finite open sets, say G alpha out of open cover G alpha. Means any open cover here, we cannot choose the finite cover which comes, because it is infinite. So, it is not compact. It is not compact. So, this contradicts our okay. So, that is what we are not going detail for this, because it is a part of the functional energy. The next result which we say is the Weierstrass theorem. The theorem says every bounded infinite subset of R k, every bounded infinite subset of R k has a limit point in R k. In R k. The proof is very easy. Since E, every bounded infinite subset, say E of R k has a, since E is bounded, which is infinite also, set is a subset. So, E is a subset of a k cell I, which is contained in R k, because it bounded means it will covered by some k cell. Okay. But what is the earlier theorem says that every k cell is compact, but every k cell is compact. Therefore, I is compact. So, E, which is contained in I, which is a compact set. Okay. And what this result says, the one result which we have already shown, that every, if you choose a infinite subset of a compact set, then E has a limit point in k. So, every infinite subset of compact set. So, if E is an infinite set of a compact set, infinite set of a compact set k, then E has a limit point in k. This we know, but we know this result. So, using this implies that our Weierstrass theorem, the proof of the Weierstrass theorem. Because Weierstrass theorem, we wanted to prove a bounded infinite subset of A has a limit point on R k. So, this completes the proof of this. Okay. Now, we have one more concept of set which comes in that is the connected set. Okay. So, let us define connected set. So, first we have a separated set, separated sets. Okay. Two subsets A and B of a metric space capital X are said to be separated if both A intersection B closure and A closure intersection B are empty set. Are empty sets. It means that is if no point of A, lies in the closure of of B and no point of B, no point of B lies in the closure of A, closure of A. Okay. Then we say these two sets are separate. It means this is the one set A and here is another set B, okay, B, not disjoint. Now, if I take the limit points of A, all the point of A, then it should not belongs to the closure of B. And if we take any point of B, all its limit point, if it does not belongs to A, then we say A and B are separated. For example, if I take this set, say 0 1 and 0 1, suppose I take the set 0 1, B is the set say 1 2. If I look this, so this is the 0 1 and here it is 1 2, this is 1 2, this is. Now, if we look what is the closure of B, the closure of B is this. So, this is our 0 1 is the set A, and when you take this, then it becomes B 2, that is the closure of B bar, which includes 1 and open at 2. But 1 is a point which belongs to only B bar, does not belongs to A. So, neither the point of B nor its limit point belongs to A. Similarly, if we take the others, say this is 0 and 1, this is the closure of this, and the open sets, this one is 0 2 1 2 1 2 is our B. So, A bar intersection B is empty and A bar intersection B is empty. Then here A intersection B bar is also empty. So, A and B are separated set. Okay. There is a difference between the disjoint set and separate one. Separated set of course are disjoint, but the disjoint set may not be separated. Separated sets are of disjoint, are of course disjoint set, are of course disjoint, but disjoint sets need not be separated. For example, if we look that interval 1 2, A is the set, suppose I take the interval close interval 0 1, and B is a set which is an open interval 1 2. Now, A and B are disjoint, A intersection B is empty. So, this implies A and B are disjoint, but A bar intersection B is not empty, A bar intersection B, because no, A bar A intersection B bar, sorry, A bar B, A intersection B bar is not empty, because when you take the closure of this, 1 is the limit point, 2 is also limit point. So, intersection will include 1. While the separate set said if both these are empty set. So, here at least this is not empty. So, this shows A and B are not separated. Okay. Now, we define the connected set now. a set E which is subset of X is said to be connected if E is not a union of two non-empty union of the two, not a union of two non-empty separated sets. Okay. So, this now one result we have in this connectedness over linear line. What he says is a subset E of the real line R1 is connected if and only if it has the following property. The property says if x belongs to E, y belongs to E, and x is less than z less than y, then z is also in E. The proof is very simple. So, I will just give the outlines. If there exists, suppose if there exists a point z, if there exists x belongs to E, y belongs to E, and some z belonging to the interval x y such that z is not in E, then we will reach a contradiction. Then E can be expressed as the union of this set where A z is the set of E intersection minus infinity z, B z is the E intersection z infinity. Okay. So, since x and y are in ways, since x belongs to A because it is in E, and y belongs to B, and A and B are non-empty, and A and B are non-empty, since this is an all non-empty, then since A is the A z which is subset of minus infinity z, and B z which is subset of z infinity. Therefore, these are two separated set. Then obviously, A z and B z are separated. So, once they are separated, then E cannot be connected set, because E is the union of these two sets. So, it is not so contradiction. Therefore, this result may not be true. This however, conversely, if suppose E is not connected, then there are non-empty separated set. Separated sets A and B such that their union A and union B is E. Now, pick up x and y. Now, pick up x belongs to A, y belongs to B, and let z is the supremum value of A intersection this closed set x y. Now, obviously, this set A clearly x belongs to the A closure, X closure, and hence this Z, sorry, Z belongs to A closure, and this Z cannot belongs to B. Okay. So, what we get? In fact, so therefore, X may be less than or equal to Z and strictly less than Y. Now, if Z does not belongs to A, then in case then we have X less than Z less than Y and Z is not in E. If Z belongs to A, then we have Z is not in B. So, we get there exists a Z1 belongs to does not belongs to E, but such that Z1 there exists a Z1 such that Zx less than Z1 less than Y and Z1 is not in B. Therefore, X less than Z1 less than Y, and this implies that Z1 is not in Y and Z1 is not in Y. So, this completes the proof. Okay. I think thank you very much.